So I want you to consider this situation for a spring attached to a mass. And we're going to take and pull that mass inwards, compressing the spring to a small amount, and pulling the car a distance A towards the wall and releasing it. Now, in this problem, we clearly have a simple harmonic oscillator, which probably right now has energy 1/2 k a squared. No big deal? Now, we saw a question like this where after it was released, the mass passed to a point where it was at its maximum velocity, and another box was dropped on top of it. Do you remember this one? We talked about this a couple weeks ago. Now, this problem is actually very similar to the question that you guys did for your FRQ, in that there was a perfectly inelastic collision, and this perfectly inelastic collision affected parts of the problem. I would say that this is an evolution of the question you were expected to do today. The one that you did today was actually easier than this. It had a perfectly inelastic collision and then went into a system of simple harmonic oscillations, and you were asked about that system. This one's harder because our object is already in simple harmonic motion and the collision happens while it's in simple harmonic motion. But when you parse it out, you realize that just this instant is the only instant that's the collision, and after this, it's still in simple harmonic motion. So let's change it up a little bit and consider a question that hasn't been asked. And that's one in which the mass makes it over to here, where we are on the other side of equilibrium, a distance A, and right when the box makes it to A, we drop another box on it here. Now, the collision occurs at the instant the lower box is at the amplitude, which does tell us a couple things. First, when we're at the amplitude, it tells us that the velocity is 0 at that moment. We know that the position of the object is at A. And my question for you is, consider this list of items. Which of these items would be affected by dropping the box when we do right here at the amplitude? And which of these would be unaffected? The answer might surprise you, so I'm willing to let you guys talk it out a little bit with your peers, because I think that you need to have a moment to consider which of these things would change and which wouldn't. You can imagine a tick box where you would ask which one would increase, decrease, stay the same, and why, with a paragraph explanation as to why. Can you imagine that problem? Because if I can, the test writers can. So I'm going to break you guys up into groups. I want you to think about this as your example, and I'm not going to take long. Let's say, let's go with like less than 5 minutes. So there we go. Go away for a minute, then come back ready to argue. So when we're looking at this, the moment that mass lands there are several things that change and several things that don't. Now, they might not be all the way expressed, but we know that they're going to change. Yes, you might have to wait to see an oscillation to see if they've changed. For example, Alex, I want to pick on you for once, although you would probably offer an answer. Can you, from this whole list of things, can you pick one of these things that did likely change due to the mass striking the other mass? How many of you guys think the period's going to change? Just give me a yes or no in the participant window. All right, overwhelmingly yes. And I think that's a good thing to think about. Alex, give me a one-sentence explanation as to why the period changed. Now, although I think that referencing the equation is definitely the most straightforward way to go, can somebody offer maybe another explanation that does not reference the equation? Go ahead, Stephen. Perfect. So I think these are two perfect explanations. I like them both. I think we need to remember that they're going to want us to be able to connect what changed because of this, the mass changed, and how does that change impact the period? Well, the period is impacted because there's more inertia now. It's harder to move, so it will take longer to move. The spring hasn't changed, so the force from the spring hasn't changed. But with the mass going up, the acceleration is going down. So these are ways in which you can explain it that don't involve an equation. I want to stay away from equations a little bit when we can, but if there's an equation that explains it, and there clearly is, there's no reason not to reference it, unless, of course, they go further and ask you to explain it without using the equation, which we know they've done. So let's go on to the next one. I'll give somebody else and I'm going to put an arrow next to the ones that we know change, and an X next to the ones that don't. So what's another one that changed? Thank you. Go ahead, Josh. All right, and can you give me a reasonable explanation as to why? Ooh, would anybody like to? You've made a mistake. So, Matt, you have your hand up, and I didn't see that you'd put it up till just now. Do you want to help him with this one? Okay, so I want to analyze both of these for a minute. And for you guys who are taking notes, there were some good things said here, and there were some errors. And the best part about the errors is, if we're trying to be in the minds of the test writers, one of the things they like to do is they like to put something out there that might sound like it's true, but has errors upon inspection. When we talk about velocity, one of the velocities we could be talking about here is the maximum velocity, correct? The velocity at which it goes through the equilibrium point. So when we talk about that velocity, I think it's reasonable to assume the velocity would be less. And because of that, we know that the velocity being less will make the momentum different. Now here's the thing that I think is hard. Josh's discussion that since the momentum would have to be conserved, the velocity would go down because the mass went up, sounds incredibly plausible and is mathematically reasonable and fits the relationship we know between momentum, mass, and velocity. But there's a problem with it. And the problem is that the reason why the object goes slower is because it has more inertia. But when the collision occurred, what was the momentum of the system when the collision occurred? That's right. When the collision occurred, the momentum was zero. This really didn't constitute a collision in the sense that we've seen collisions before. So during the collision, after the mass landed, the momentum was still zero. Not because momentum was conserved, but because nothing was moving. The reason the system gets momentum is because the spring acts on it, which means ultimately the velocity at max is going to be less and the momentum is going to be less. Because although the system has more mass, it's going to be traveling slower, much slower. So it's very unlikely to have the same momentum as it had before. Now, I don't know this one without actually checking. Numerically, it could be the same momentum, but I have reasons to suspect it won't be. And that has to come down to the last one. And here's where I want to see if somebody got this one or not. Can somebody speak to the kinetic energy? You're trying to redeem yourself? Well, I want your redemption, but I also want to see if I can get more people to speak up. So let me see if I can get somebody else to speak up, because Josh, you didn't do a good job. Go ahead. Let's see what you got. And why would it decrease? All right, let's see this. In the participant window, because we're getting to the edge of this question, tell me yes, that you think the kinetic energy changes, or no, the kinetic energy doesn't change. Do you guys see the totals when people do this? Or am I the only one that sees the totals? Because it is almost 50-50. So we've got, it's 11 to 14, 11 yeses, 14 nos. So, it went to 14 to 15. So basically, we don't know the answer. Half of you say yes, half you say no. So I'm going to let Josh speak to this. Maybe he knows something here. Josh's answer here is perfect, and you get full redemption, buddy. That's it. The amplitude doesn't change. And all of the energy was in the spring when this collision occurred. So the amount of energy in the system isn't going to change. However, its expression because of velocity will change. So the mass goes up. The velocity is going to go down by an interesting amount because the velocity is squared here. And we don't know the impact that's going to have on the momentum. It's likely to change, but probably not in a way that we can predict easily. But yes, in this system, the energy did not change. We just suddenly had an increase in mass. So I really like this question because I find it to be, it's not mathematically cumbersome. It really involves a lot of the information from the semester, and it creates a unique situation that we had not thought about before. And I think it's this kind of question where we're doing this kind of explanation that might be a reasonable kind of question to expect from AP. Anyways, I like it. It was good stuff. Good conversation case. I think that they are going to maintain an exam that's more heavy on text explanation and less about calculation. This exam for years has not really been about calculation. You've seen that in the practice questions I've given you. And although I like to have a good balance, I think a problem like this could be very heavy on explanation with very little to do with calculation. Does that make sense? All right. Well, guys, we don't meet officially tomorrow unless you need some help with your homework. If you do, definitely find me. I'll be ready and raring to go right around 10 o'clock. Otherwise, have a fantastic weekend, and I will see you all on Monday. It's been nice seeing you all today. I'm going to miss the fact we won't see each other for like 3 days. It's going to be tough. But I look forward to our little meetings. I love seeing all the people in the boxes. That part's a lot of fun. So have a fantastic day, guys. Bye-bye. Bye, guys. Yeah. What's that? Yes, today is my birthday. Yeah. Well, you're swell. I appreciate that. Thank you. Yes, it is my birthday. It's going to kick you all out. I know. It was perfect. Oh, you got it all in on time. Thanks, guys. That was awesome. It was perfect. It was perfect. Yeah. You're making cat noises?
No, it's someone else. I guess recorded their cat making that noise, and so they were like, use this on your cat and see what they do. So and it started repeating, and she's still kind of looking around.
That's pretty funny. Pretty funny, girl.
It doesn't have any legs though.
Well,